Okay, the shaft shown on the side has the inner and outer diameters of 4 inch and 6 inches respectively. The maximum allowable shear stress is 12 ksi. Find the maximum torque that can be transmitted by the shaft without failing. So let's see what's given. We're given tau max is 12 ksi. We're given the diameter of the inner the inner diameter, which is 4. So if you want, you can compute the inner radius. It's half of the diameter, so it's 2 inch. And then the outer diameter is 6. Inch. So the outer radius is 3 inch. Okay, so what we are asked is the max torque that this shaft can bear without failing. So what we know about a shaft with a inner and outer diameter is that this is the distribution of torque of the shear stress. There's a max shear stress on the outer side, the min on the inner side. So clearly the maximum occurs at the outer side. So that's what we should be focused on. So we need a formula which gives us tau max in terms of T max. And if you go back, if you can actually see that, I think I've not given you the formula for, well, it's very general. Okay, so not a problem. So here is the formula, which it basically gives you the formula for the shear stress, but we're interested in the maximum one. So it's tau max is Tc divided by J. So let's use that. So tau max is T max C divided by J. Because the maximum stress is 12. Well, let me just put the formulas again. So C, okay, the C is what? It's the outer radius, right? So it's not the inner one because the maximum stress occurs on the outer one. So I need to put C0. Next, I have J. Now J comes from the table. The polar moment of inertia for a shaft with the inner and outer diameter is pi divided by 32 d0 raised to 4 minus di raised to 4. Where did I get it from? It's from table A18. Okay, let's pull this up. Yeah, I think it's one of the. Okay, so you can see this Jg, that is the polar moment of inertia. So here it is, pi d raised to 4 divided by 32. This is for a solid shaft. If the shaft is hollow, then well, you have to use this formula. Here pi divided by 32 d raised to 4 minus d raised to, well, capital D raised to 4 minus lowercase d raised to 4. That is because capital D is here clearly the outer diameter, d small d, or lowercase d is the inner diameter. So this is the formula I used. Yes, so that's how I wrote it, pi divided by 32 outer diameter 4, inner diameter raised to 4. So let's sub in the values. Okay, tau max is given to us 12 psi, T max is unknown, C0 is, it's here 3 pi divided by 32, outer diameter raised to 4, inner diameter raised to 4, so 4 raised to 4. And so the only unknown is tau max. Solving for, by the way, if you want to check, this thing comes out to be equal to 102.1 inch raised to 4. It's an intermediate thing, can check. And then we have solving for T max, we have 408.4 kip Okay, shaft AB and CD are solid of diameter D. So let's see, AB. So this is the shaft they're talking about, and CD, this is the shaft, is solid of diameter D. So there's only one diameter D. Okay. While shaft BC, so this one, is hollow of inner and outer diameter of 90 and 120. Okay, so you don't quite see it hollow there because you cannot, it's not cut at any point between B and C, but it is hollow. The shaft assembly is subject to torques as shown. So it's subject to torques as shown means these are the torques showing up on the different parts of the shaft. Compute, or first case plot, the torque as a function of shaft length. Compute the maximum and minimum shearing stresses in shaft BC and the diameter D if the allowable shearing stress in shaft AB and CD are 65 MPa. So we need to compute this last question. Okay, so the first part is actually interesting, which is plot the torque as a function of time. So this part is actually very similar to what you have done in the past for shear force diagram and bending moment diagram. Okay, instead of drawing shear force and bending force, you're going to draw a torque diagram, which is be essentially the torque as a function of length, okay, whatever that curve is, however it is. Just putting something. Okay, so we need to figure out what this curve is. Okay, and actually that's important because if you don't have that torque as a function of length, you do not know where the maximum torque occurs, and if you don't know where the maximum torque occurs, it becomes hard to compute the shear stress, and that's why we need to do number one before we can do anything else. So let's get to one. Okay, now the way you do one is you can actually cut the shaft at various points. So you can see there's a torque at A, there's a torque at B. So between A and B, you can cut the shaft, do a free body diagram, but it'll be a diagram which will help you to figure out the torque, put the value for the torque, and then move to the next section, which will be here, and then you have the torque diagram. But for this problem, it's actually kind of straightforward to do it without doing all that, because it's constant torque. So let's try to do this without actually drawing any free body diagrams. Okay, so we can start from the left and work our way to the right. So from A, so we have a torque of 6 kilonewton meter at A. So this is, let's say, A. So that's our origin. So we have 6. So let's say this is 5. So 6, 6. So it spikes to 6. And then it's 6, but remains 6 all the way to B because there's no change in torque between A to B. So it remains 6 up to B. At B, what happens is there is a torque A 14 kilonewton meter, but you can see that this torque A, well, we assume that in this case, we just assume that clockwise positive. Like I really don't have a specific notation here, but if you, well, sorry, it's counterclockwise. As you see it from here, my bad, it's counterclockwise, and I think the convention is counterclockwise positive is always safe to do it that way. So counterclockwise positive. So this is counterclockwise, so 6. And then there is a torque of 14 at B, which means that this torque of 14 will add on to the torque for 6. And so you'll end up with 14 plus 6, which is 20. Okay, now from B to C, there's no additional torque. So we just keep going with 20 till we hit the point C. At C, you see that there's a there's a torque of 26 kilonewton meter, but it is in the clockwise direction, which is opposite to what we had so far. So you need to subtract 26 from 20, and so you'll end up with minus 6. So we go all the way down to minus 6. and then it remains -6 till we reach D. At D, you see there's a 6 kilonewton meter torque acting in the counterclockwise direction. So I need to add 6 to -6 and I end up with 0. So at D, the torque is again 0. So this is my torque diagram, torque as a function of distance x, and it'll be needed later on. So we have that. Okay, next, let's move on to the next question. Compute the maximum and minimum shearing stress in shaft BC. So remember that BC is the hollow shaft. So number 2, so let's draw a cross section of BC. Okay, so we know that the stress would be something like this. This would be tau max. This would be tau min. Okay, so what tau max is, it's, we can go back to the formulas. I think it's the torque is T rho divided by J. So T rho is going to be the outer diameter. So sorry, outer radius. So C outer divided by J. And then we can write tau min is torque C inner divided by J. Okay, so with that, we can now start subbing in values. Um, what is T? T is the torque on the shaft between B and C. So it's clearly 20. This comes from the diagram, from the torque diagram. 20, is it kilonewton? I think it's kilonewton meter. Always a good idea to write the units here. Okay, C outer for shaft BC, it's over here. For BC, the outer diameter is 120 and the inner diameter is 90. So outer is 120, so half is 60. Inner is 90, so the diameter is 90, so the radius is 45. Okay, and then J is okay, so J comes from table A18. It's pi divided by 32. The outer raised to 4 minus inner raised to 4, where the outer is clearly 120, the inner is 90. Okay, so at this point, we have identified all the unknowns, T, C0, C1, J. Just a matter of plugging in the values. So I'll just give you uh, the answer, and then you can check it later. So the answer I got is, this is an intermediate value to help you check. I got J as 13.9, 10 raised to -6 meter raised to 4. Tau max is 86.2 megapascals. Tau min is 64.7 megapascals. That's my final answer. Okay, with that, we go to the last part, which is we need to now, this is a design problem, compute the diameter D. This would be in shaft AB or CD if the allowable stresses in shaft AB and CD are 65 MPa. Okay, so we're given the maximum possible stresses in AB and CD. Now, one thing to note is the part of the shaft which will have maximum stress is going to have the maximum torque, right? Because the shear stress is proportional to torque. Given that, the formula for this is really T rho divided by J. Yeah. Okay, so what we see here is since both the shafts have the same diameter, that would be the same for both of them. J is going to be the same because it's a property of the geometry. So eventually the maximum torque will occur where the the maximum shear stress will occur where the torque is maximum. So for AB, we see that the stress here is 6. For CD, it's -6. So both of them have the same torque. So you could use either of them to design for the diameter. Now, if the torques on one part, AB was say 10 and was -6 for CD, that means that AB has a higher torque than CD, which means that you'll use AB to design the diameter and not CD because maximum shear stress will occur in AB. Okay, so that's something to remember. In this case, it's inconsequential which part you use, AB or CD. So AB and CD. So part 3, AB and CD will have the same shear stress because they have same D diameter and the same torque, which is 6 kilonewton meter. Okay, so we could use either of them. So the shear stress in AB or the shear stress in CD is the same. It's T C divided by J. The torque is 6. Sorry, move it back. I think we can put the maximum value. It's 65 MPa. The torque is 6 kilonewton. So 6 times 10 raised to 3. The radius is D divided by 2, a design parameter. And then J which is the polar moment of inertia for a solid shaft, is pi T raised to 4 divided by 32. This comes from table 18. Okay, so the only unknown here is D. If you want, you can cancel this D with this, get 3, and then solve for D. Something like 6 times 10 raised to 3 divided by 65, 10 raised to 6. So you have 32 divided by pi. And then you need to take the cube root of this. Okay, so solving for D, I get 77.8 millimeters. That's the answer.